Start recording. All right. Where we left off. Let's hang on. Where did we leave off? We were solving this problem where we layered a whole bunch of shapes, and they all, if we separated them, you know, they all try to either separate at once, or we end up in this position where they all like separate really slowly. And we were trying to deal with that. And so the thing that I'd left you with was, okay, we are separation, calculate separation. Okay, we are here. We have just added the intersection count, and the concept was, all right, if you go off and think about this for a bit less than a week, can you come up with something that, some operation that lets us separate, and how did I put this? Basically, we had these constraints. It's like we want to go as far as possible into the separation as we can to like try and resolve the separation. But we definitely want to avoid separating out too far, because you know once we're in like the position indicated by the pink arrows, you know we're just way off the map basically. And the other constraint that we had is, you know, we want to do as little work as possible, and that means as little work as programmers and as little work sort of CPU and memory wise as well. So first question would be, you know, did you come up with anything better than what we had last time, which is like just multiply it by 0.5, or do something a little more complicated, which is the length of the separation divided by the radius as a scaling factor?
Yes and no. I mean, I did think about it. I don't think I came up with anything better than the scaling factor, other than okay, so the thing I thought of was, why not, like, we have, so the thing at least we had was we have the count of you know, so basically take the, I guess, the mean of both of the separations for either one and cap it at the largest value, and then split, like basically rather than do it all at once, just do it, look for everything that's greater than one connection and or one overlap, and then split that one by the mean, so they both go a little bit closer towards their goal. And maybe the next time they'll still be overlapping, but at least it won't be like an arbitrary scalar, which kind of messes with gameplay. But I don't, the reason why I don't know if that's even that valuable is just because, well, maybe now we still have to track. Like I keep going back to the idea where we have to kind of like have the values of each of the separations for each of the overlaps.
Yeah, so you've run into that thing where we have like an n squared problem. Is like suddenly you need to store like the fact that these two are intersecting, and the fact that these two, and the fact that these two, whereas I mean for 3 it's obviously still 3, but you know, we add a fourth one and suddenly it's like, okay, we have 4, or we have 1 2 3 4 5 6 7 8 9 10 11 12 and so on.
Yeah, so I wouldn't, and I was gonna Google it, but I decided not to do that too. So just to use my own poor brain. But I couldn't come up with anything better than what we've got. That would be just like functional, like without storing extra data.
I'm not sure that Googling it would really do much, because it's sort of an esoteric problem. But I think you were onto something with like take the average. Like that's an interesting path to go down. So I think like let's.
But where do we get the average from? Like, well, we need 2 values to derive that. Do we have them?
Well, we are accumulating. So pending separation, we've added together a whole lot of things. Let me try drawing this in one dimension. So let's pretend we're in 1D. And what we've come up with is we are reducing ourselves down to, we have a bunch of so we're only looking at one shape. We're going to ignore the fact that other shapes are involved. They're just giving us like a list of separations. So it's like, all right, we have a separation out that way, and maybe we have another separation out this way, and maybe we have a separation out this way. In fact, actually, I'm going to... we could have a separation out that way, but I'm just going to simplify matters and say we have them all in the same direction. And so what's happening is we're adding that all together, and that's giving us a separation out that much, and then that much, and then that much. You could imagine, you know, if we have that separation and that separation, we add them together, and we get that much plus that much. So we're going that far.
Right.
So that's what we're doing at the moment. So we're adding them together.
Right, but we're doing that in calculate separation. We're not currently getting those values. Like, we're not getting all three pieces. We're just getting the sum.
Exactly, and that's saving us a lot of memory, basically. So we don't have to store a list. So the thing that you said that was interesting is, you know, we could take an average, because we have the total. So we have this.
Mm-hmm.
I'm gonna keep that red because I lost my undo buffer again. Okay, so and we have like the number 3, and this one we have the number 2.
So just divide by that.
So we could just divide by that. So then we end up with. I have to draw this very carefully. We're dividing by 3, so we're getting this distance
right,
here.
And the danger, though, is just that like that distance is actually larger than the third segment, and so we run the risk of separating more than one of them would have.
Well, I want to draw your attention to something very interesting about this particular case, and that is. I want you to think about this problem. Let's start with this. So say we have a bunch of distances like that and that and that and that and that, and we want to add these all together and divide them. So as sort of a first step, if we sort these by size, so we're like, all right, big, and then sort of smaller, and then sort of that's about the same. That's roughly. So if we sort them by size, and then we like concatenate them like this, so we add them all together. When we sort them, it's always going to be the case that the average, so if this is getting divided by 5, division by 5 is hard, it's always going to be the case that the average is smaller than the largest one. So yeah, is less than or equal to.
Right, but I was referring to how it could be larger than the smallest one.
Well, that's actually fine, because you can imagine now we step back into the problem that we were having. If these are shapes, I've run out of space. I'll redraw it. So if these are our shapes, like small, medium, large, so and we go into thirds. So in fact, it is very likely, in this case, you see that third, definitely larger than this one. That's actually quite likely that it's larger than the smallest item. I think it's also the case that average is greater than or equal to smallest item.
Yeah, that makes perfect sense. So I dismissed the reason that I dismissed my own idea was because I thought we would have to store or do another stack alloc to get the smallest and the largest because of the fact that, like, again, just that we would be moving one of these objects. We would likely move one of these objects further than it would have gone on its own.
So
to separate.
So pretend this item is like a zero-sized item. The thing that we're separating is zero-sized. And these are concentric circles. So we're simplifying the problem a bit. So it's like, all right, if we separate out the small amount, we're still inside. If we separate out the medium amount, we're still inside. If we separate out the large amount, that's actually what we want. We actually want to separate out by the largest amount. But there is an issue there, and that is we lose some directionality, as we were talking about. It's like these are not necessarily concentric in the actual problem space. So separating out by the largest one just arbitrarily is kind of not ideal. We could do it, but then we also have to track that state, like largest by magnitude here, and I think it can result in issues. It might work, but the thing we can do is much simpler. It's like, all right, well, we can take this orange arrow here, and if we separate out by that much, we're fulfilling sort of the goal. We're guaranteedly not separating out too much.
Yeah, I had it backwards because I got in the mindset of, like, the separating axis and think about the minimum distance. So it sounded like a problem, but you're right. We actually want to push it out to the edge of the largest overlapping object, and the average will never be bigger than the largest one, so it actually works out just fine.
Yes.
So, yeah.
So this is sort of like, this is one of these unfortunate things that it's those interview questions they do for like Google and stuff. It's kind of like an aha thing. It's like, so like it's like I wouldn't concern yourself by, like, not having come up with that. That could take months to come up with, just because you just haven't made that mental step.
Right.
So I guess the best thing you can do in these cases is to expose yourself to a lot of problems like this and a lot of maths, and just like think on these things for a while, which is kind of what we're doing here. So anyway, the nice thing about the solution is it's dead simple to program. So in fact, I'm not even gonna. I'm gonna leave this to you. So, all right, we're gonna do an average. We have a total and we have a count. What do we do?
Yeah. Divide them.
Yay! Yep.
Yeah, that's it. Just divide them by the count when they're greater than 1, and then call it a day.
Well,
although you've got the different thing in yours.
Oh, I've got that garbage.
Okay,
That was just a test. We can go even one step better, because if it is equal to 1, we know it's not equal to 0, because otherwise we wouldn't be in here. But if it's equal to 1, we can just divide by 1.
Oh, true.
So that's another way to get to that point. Is like, well, actually, in fact, yeah, that's worth discussing. So when you have a problem like this, and like that, in fact, I think that's sort of the that helps you get to the in these problems. It's like, all right, if I have a case where I could have like 5 of these, or I could have 3, or I could have 2. What do I want to have happen if I have 1? And if what I want to have happen when it's equal to 1 is just to evaluate that thing on its own, then it's a useful thing to think, all right, well, what if I divide by 1? I guess that's kind of abstract. Like, it's a mental technique that I have trouble putting into words. But yeah, it's like I want to preserve the single item case. So can I do a division by the number of items? Because that 1 is always going to just leave this case alone.
Right.
Yeah. And that's sort of
that makes sense. If I put my pedantic, silly .NET hat on for a second, the dividing by 1 includes also a array access. Is that going to be more expensive than the branch on the count, which also includes the same array access? Like, I'm just wondering, like, you know, from a completely not even necessary to think about optimization point of view, which one is more expensive? And you're going to tell me that it doesn't matter. Dividing by 1 is basically free.
Have we looked at... I've lost all my favorites after...
Oh, right.
So I'm going to just quickly Google this thing. Have we looked at this?
Yes.
Yes. So that's terminal. I'm not sure what division it's going to use, but let's pretend this is actually optimized well, or something like well. Well, first of all, actually, that's the first thing I'd say, and that is if you were optimizing this using SSE instructions, you'll recall we were talking about the way that you do the data layout is like, rather than having, you know, in memory, it's like, you know, X comma Y and then X comma Y, you know, you'd have a block of like X, 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 and then like Y, 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 Y.
Right.
And then you'd load each one of these into a into like a wide register, and then you do the operation like, all right, you know, that divided by that. Am I scrolling out of capture range? Yeah, you do the division, and then you'd get out the result. It's like, all right, is you know, A, and you'd get 4 divisions at once. So already from this perspective, in sort of a real world scenario, you would want to avoid that if statement because it lets you do this.
Right. Yeah, that makes sense. And also, like, we're doing so little things here that we probably would fit into the same register anyway. So the divided by 1 might be free in that sense. If we're
well, no, that's so that's registers and yeah, that doesn't really have effect on register allocation and stuff. But okay. CPU wise, so this is why I brought this up, and then I'm like, hang on, if you're actually streaming it, you'd want to get rid of the conditional anyway. But what am I looking for? MM div. So it could be the case that it's divide the single lower processor. So I have no idea what the compiler is going to spit out, but it could be a single division. And then we can look up, okay, what's the latency and the throughput? So let's pretend that the compiler is outputting just crap instructions, such as this. So we have to do 2 of them. If we have to wait for them, it's let's pretend we're on Ivy Bridge. So let's say it's up to 14 instructions. It's going to be late. And then we're doing another one sort of in parallel. So we're actually up to about 20 instructions for the division.
Okay.
And that will be extra instructions. I guess it's a bit fewer because like the addition, for example, that we have here will overlap the overlap some of these divisions probably.
Yeah, that's what I thought I was thinking when I was saying that. Well, if it's divide by 1, and we're already doing that other thing and want to fit into
Hmm.
the yeah, I have a very tenuous grasp on that, but
So let's just pretend that this is going to take an extra, because we have two divisions. We've got six instructions. This is cycles per instruction. Sorry, so I shouldn't say instructions.
right,
We've got 6 cycles per division, so we've got 12 cycles extra to push these through the CPU. And it might be a little bit more. It could be up to 20. So the question then becomes, all right, what is the mispredict on a CPU such as Ivy Bridge? I don't remember. I think it's probably around 20 in cycles. Maybe it's less. Maybe it's like 14. So what happens is if it mispredicts this branch, so if it starts executing this one, it's like, oh, I'm gonna branch over here. And it's like, oh, that was a mistake, and has to clear out the instruction pipeline and start running this one instead. It's going to waste, say, 14 cycles doing that. And then
right,
it has
and the division is always only 6.
then it has then it has to go and spend 12, because keep in mind there's two divisions happening here because this is a vector.
Oh, right.
And so yeah, if it mispredicts, you're just getting the extra hit from the misprediction, plus you still have to do this. So it's actually, I think it's probably always more. But if it always predicts correctly, so if you can say, and this may actually be the case, that it's almost always going to be an intersection count of 1, the branch predictor is always going to go here. It's always going to skip this. And if this case never happens, the branch itself is pretty much free, because the branch predictor predicts it, and then in the future, like after the prediction, it checks its prediction. But and that will use some CPU resources, but that will happen more or less in parallel with all of the floating point operations. So we've got like an integer branch check happening in parallel with this addition, and it's like, I did take the correct branch, and so it just keeps going on its merry way. And we know for a fact that our data is almost always going to be the case that the number of intersections is going to be 0 or 1.
Yeah.
And so it probably is actually faster to do it this way, oddly enough.
I win.
But this is an odd case. And yeah, like, and that's roughly what it should do in the branch prediction case. On like an older CPU, where you didn't necessarily have all the branch prediction magic, this one would probably be better. But it's really iffy to write code in that way if you don't know what you're doing and you don't have the test cases to profile it.
Yeah, I know. I was mostly for conversational sake because.
No, it's an interesting thing to look at, and I just want to look up the. See if I can find this image. Sorry, I'm just over here on my other monitor looking for a picture. This is these are not the pictures I was looking for, but they're rough approximations of them. Okay, that'll do. All right, so this was the diagram I was looking at. It's like, all right, if you get to here, or here, and find that you took the wrong branch, you have to like trash everything and come back to here. It's really not the diagram I wanted. Oh well. Anyway.
I think you tried to find that in another video as well.
I think you've probably seen it.
we saw it on one video, but then yeah, I think this is our second attempt to re-find it. We'll have to find that and paste it for posterity somewhere.
Yeah, yeah. Like if you want to go really deep on this, and I think this is where I saw this diagram. It's like, that's exactly the diagram I wanted. Someone who actually is very good at this particular topic is Fabian, and he actually does these talks. Like this should look familiar. In fact, this that we just had a look at, and he actually brings up the same diagram. He goes into like insane detail about what a modern CPU does and like how the circuits are built and stuff. And so if you've got a spare 3, 4, 5, 6, 7, 8, 9, 10 hours, that's a useful thing to look at.
Excellent. Yeah, the other thing that I wonder about sometimes is the sort of assumption, like the kind of thing where you hear it once and then you don't actually question it, is that multiplication is always more efficient than division. And you're always supposed to kind of like restate your problem as it, don't divide by 2 when you can multiply by 0.5. But I don't know, that's not in scope for today, but it's another thing that's useful.
Well, it's actually actually a question we can answer really easily. So if I go mm mul ps, a multiplication has a latency of 3 and its throughput of 0.5, so you can actually do 2 of these in parallel on Broadwell and Haswell. And that's mul, and we just looked at div, div ps, so that has a much higher latency in structures. It's 8 times slower, roughly speaking.
It's interesting
to do division. So it is in fact the case that multiplication is better.
Okay, at the like down at the bare metal, but I guess I'm a little surprised that like the CLR, like the optimizer, wouldn't automatically replace your divide by 2 as multiply by 0.5. Like, I'm just wondering, does it make it all the way up to like a developer's conscious like need to think about it, or is that something that gets kind of, I guess you'd have to kind of crack open IL and see for yourself whether it makes that change for you.
I feel like there's a weird political thing that went on. Like, I don't know what the current state is with .NET Core and stuff, but yeah, there was this weird political thing within Microsoft where the compiler team is like, oh no, we don't do any optimizations at the conversion to IL level. We just say we spit out the IL and expect the JIT to make all the optimizations at JIT time, like when it's running on the user system.
Right.
And then the JIT team's like, well, either we don't have the spare JIT cycles to do that, or we have a whole lot of other stuff we have to do. And so yeah, the compiler team's like, oh no, we'll let the JIT do it. And the JIT team's like, oh, we haven't done it. And so that kind of optimization doesn't necessarily get done. There's also possibly, and I don't think it is the case with the division by 2, but that's sort of like an unusual thing. But it is possibly the case that if you actually care about the result of your floating point arithmetic, which probably more of the users of .NET care about than the speed, and that is you actually might end up with different results by like the least significant parts of the result, like the floating point result, will be subtly different whether you do a division or a multiplication. So it can actually matter mathematically.
Huh. Oh yeah, that makes some sense. It's also right, and because there's all the different runtimes too, you're gonna have a real problem with like .NET Core if you do that optimization on Linux and Mac.
So let me show you. let me see if I can find a sensible. I've just Googled. What is it? So. I don't know. I can't remember what any of these flags are off the top of my head, but in like this is Stack Overflow result. That's fine. So there's this fast maths flag. Here we go, and then Visual Studio's floating point precise versus floating point strict versus floating point fast, and so on the native compilers for C++ and for GCC and Visual C and so on, there's actually flags that will toggle what you want the floating point compiler to actually do. Do you want it to throw caution to the wind as far as accuracy goes and make it as fast as possible, or do you want really, really accurate results that match what you typed exactly?
So it's not something that you can really rely on then when you go to compile, because again, because you're saying it's basically just too many choices and too many possibilities of it going wrong.
Well, I suspect that in C++, if you have if the fast turned on and you write something like float foo bar, like if you write foo equals bar divided by 2, I suspect that if you are in fast floating point mode, the compiler will actually do. The compiler will actually output that one. I think in .NET, because it doesn't have this sort of thing, it will just do the safe thing.
Right.
But I don't know what the modern .NET compiler will do, because I haven't looked at it for a while. But certainly, if that's what you care about, you're writing C, and you're using SSE, and you're just, if you're using C#, you're using interop to get to it. Like we sort of we left that door open on River City, although we never actually used it.
Right, I remember. Now it's just a warning every time you open the solution. You've got SIMD instructions somewhere. Or...
Yeah, whoops, that project had an issue, and that's probably safe to delete at this stage. Because for any River City fans who've managed to make it to episode 47 of this series, we're like, oh god, we may have to actually rewrite a whole lot of our functionality in SIMD, because it's, even though it's like running at several thousand frames per second on my system, is running really slowly on like a couple of people's systems, and then after a lot of like being frantic about that and annoyed, we find out it's like, oh, it's because Windows is doing something silly and just needs to be rebooted on the customer's system. It's like, thanks Microsoft, good job.
Yeah. There's also some issues. Well, Windows 10 too, right? There's a lot of but that's like.
Oh, it was exclusively a Windows, I think 8 and 10 issue, like something stupid.
Well, eventually a product that's not supported anymore, like XNA 4, is eventually going to run into a critical bug on a new operating system. Oh, that's inevitable. That's a different problem. Yeah,
that was a different problem, but yes. Yeah.
But that kind of just drives you towards things like FNA, which obviously you're thinking about the future on future hardware.
Yeah, well, if it breaks, we can actually have the source code. We can fix it.
That's right.
Anyway, all right. I think we'll just finish up. We'll seeing as we have this code, we may as well go down to the drawing method and just do the same thing, and then we'll call it. So. So this was shape.position plus pending separation. Where do we draw the arrow?
I've lost you.
So, yeah, so I've just added this new position here.
Wait, I'm just waiting for my.
Your modern computer system to catch up.
Your older one. Yep, that's right.
So appalling. And then we actually
I gotta
need
do
it
something
twice.
about it at some point. I may actually install Windows 7. That might be what I do.
It's only got when it's sometime in 2020 because I looked it up. It runs out of support. I don't know what Microsoft's going to do if it's going to XP it, because I know XP got an extension.
Oh, okay, same thing here.
Yeah, same thing there. Just to keep our diagrams in sync, and I mean, we've copy pasted some code, but yeah.
Okay, I think that's right. Am I missing
So one more
anything?
just here.
Oh, yeah, okay.
And in fact, also the next line too, which I've missed on mine as well. There we go.
Yeah.
Oh, you already have
It's
new
gonna
position.
be.
It's already in scope.
Oh, right. Gotta add it here and then here. Okay.
Let's see if that worked. So now the diagram should match up with what actually happens.
Well, you're just bragging now. My machine's still building.
That's atrocious.
Wait. Oh, is it? Oh, there we go. Oh, it's still. Oh, I see. I was actually running in real time. I was still going.
Oh, have you got
I
edit
didn't-
and continue working?
Apparently, I
That's
didn't.
good.
That's not nothing I did. Maybe I clicked it some other day.
Oh well.
Come on. See, now I don't know where it is anymore. I'm waiting for something to happen,
Oh dear.
and I don't know what's happening now. Oh well, yeah. Oh, there it is. Yay. Okay.
Oh boy. All right. Anyway, so
Oh yeah, that's a lot better. That's like. Oh, actually, is this wrong? Wrong? This looks wrong.
no, that's right. That's actually correct. So you've got a whole lot of overlap shapes. So that and they're not separating as much. So the division is reducing the amount of separation substantially.
Yeah.
So that's correct. And then we have a few iterations to clear that out, and you'll notice that it separates this whole stack. Certainly gets to this point in just a handful of iterations, and then we have this problem here, which is like
Yeah.
these
There should
tiny
be a minimum.
intersections. Well, I don't know what you do about that. I think, did one of my shapes just disappear? I think
Yeah.
we might have a bug.
Possibly.
That might be a fun thing to debug. Oh dear.
There it goes.
I think we have a numerical problem.
Yeah.
Um,
We can maybe take that on next time. Maybe I'll take a look at it myself as another independent thing.
Hang on, I think I know what the bug is. I think I know. You know what I was saying about, we don't need an if statement there.
Yeah.
All right,
No.
so while we're still on stream, let's just fix that, because I can tell you exactly what that is. I mean, you know, because you're a clever programmer. You're like, yep, we've done a division, and we haven't thought about whether or not we're excluding the zero case. So
Separating it to somewhere.
we're just adding on
Or let's just.
garbage. So, all right, that's good catch. That's better. So,
I like that you also can't see the snap either. Other position was sort of like as soon as it popped out of the as soon as the intersection count goes back to 1, it would like chunk its way out. But this one is a lot smoother.
Yes.
That won't really happen visually.
So this does have the unfortunate still issue that, I mean, the other one had that problem too, but it's like they have just this tiniest numeric sort of overlap, so they still think they're in contact. But
will they not settle? Like if you keep separating right now, are they just gonna jiggle?
Well, what's probably going to be the case is like this is probably not even that they're overlapping still. It's just a numeric problem. The amount that they're overlapping is extremely small, so the amount they get separated by is even smaller. And it's the amount is so small that it doesn't move the position enough to resolve it. So I could probably just sit here doing this for ages and it will never resolve. And so what a proper physics engine will do, and if we get down to talking about how floating point numbers are represented and stuff, we may actually do the work to basically say, all right, these shapes haven't moved for however long, so we're just going to put them to sleep. So this is what a lot of physics engines do, is they like track how much a shape has moved over a number of frames. And it's like, all right, well, it hasn't moved, or it hasn't moved within some error bounds, so we're just going to pretend it's stopped.
Oh, right. Yeah, like that's some kind of like epsilon value that
pretty much
you kind of use to fake caring about rounding error without like actually messing with it.
Yeah, so this is not a mathematical problem. This is a floating point numeric problem.
Right.
So
computers problem.
Yeah. So there's nothing we can really do to fix it at this level, but that's fine. So I think that's all we really wanted to do today.
Yeah, I'm surprised we managed to take a one line, like literally one line of code, and make a whole episode on it. So that's pretty impressive.
Yeah. Well, you can dive pretty deep on these things. I did have a bit more, but like for the people who are watching on YouTube, we actually did have like half-hour chat pre-stream about other stuff. So we will come back to stuff next time, and so next time we're going to look at collisions. So won't that be fun? All right, thanks for watching, everyone.